Italy. It's a place that means so much to so many. The art, the culture, the beaches, the mountains. Italy is a skinny boot thrust into the blue of the sparkling Mediterranean, with the island of Sicily like a ball balancing at its toe. But Italy hasn't always looked like this. It is a turbulent land geologically and has changed tremendously over time. Since the days of Leonardo da Vinci, scientists have struggled to learn what makes this land so dramatic, so unusual, so violent. This is the land that gave birth to the science of geology in the 17th century. Ever since then, geologic discoveries made in Italy have rocked our thinking about our planet.
Vedi, Sandro?
It's a sunny day in early spring.
Cominciamo un rilevamento qui, no?
Okay.
American geomorphologist Frank Pazzalia is working on the Mazzoni River in the Apennine Mountains. With him is an Italian student, Sandro Mariani.
1,22 m.
Sì.
Ok, Sandro, sei abbastanza distante.
Riesci a vedermi?
Sì, sì, perfetto.
The grandson of Italian immigrants to the U.S., Frank is intrigued by the complexities of Italian geology.
Vabbè, il canale non è grande.
Canale molto
He's
stretto.
working in Italy as part of an international team of earth scientists, hoping to add some new pages to Italy's fascinating, unfinished geologic tale. Specifically, they would like to answer a question that has been nagging at geologists for years. Are the Apennines still growing? Or are parts of them no longer active?
There's an opinion among many geoscientists that the front of the Apennines are dead, that they are no longer growing tectonically. Now, this is not shared by all geologists. So we've defined for ourselves here a very ambitious project, trying to understand the growth and the evolution of the Apennine Mountains. And in doing this and trying to understand this particular mountain range, we hope to be able to say something more general about how mountains are built throughout the world and how the lessons that we learn here tie into the general theory of plate tectonics and the construction of great mountain ranges.
The groundwork for understanding Italy's mountains had already been laid centuries ago by scientific pioneers. It was here in the Apennines during the Renaissance that Leonardo da Vinci, and later Nicholas Steno, studied fossilized seashells. They realized that these were the key to understanding the growth of these mountains. The word geology itself was invented in Italy in 1603 by Ulisse Aldrovandi. For Frank Pazzalia and his predecessors, Italy is a most rewarding place to study mountains. Some 75% of the land is mountainous. In the north are the highest mountains, the Italian Alps. Heading south, the Apennines form the backbone of Italy. They run down the entire length of the peninsula and into northern Sicily. Where the mountains reach to the coast, limestone cliffs rise steeply from the sea. The colorful towns of Cinque Terre in northern Italy are stacked among these cliffs. The Apennines meet the sea again in southern Italy, making for stunning scenery on the Amalfi coast. From Sicily to the Alps, Italy's mountains are a steady presence. And for the most part, it's obvious to geologists that the bulk of the mountains are actively growing. In fact, in some places, as Frank Pazzalia and his colleagues well know, they are growing unusually quickly. One of the fastest rising mountain ranges is close to a city known all around the world for its Leaning Tower, which dates from 1173. Pisa is also a vibrant center of learning and has been for hundreds of years. Just down the road from the Leaning Tower, Giancarlo Molli is a geology professor at the University of Pisa, where Galileo taught in the 16th century. Today, Giancarlo and his students are discussing the nearby mountains that are rising so quickly. They are called the Alpi Apuane.
Questo da dove viene, secondo voi?
Much of the geologic story of the Alpi Apuane has been pieced together by Italian geologists over the years. But Giancarlo is determined to fill in the blanks. Mysteries remain as to how fast these mountains have risen. Giancarlo wants to know exactly how fast and why. These are the mountains that brought up from the depths a very rare and exceedingly beautiful rock. That rock is the famous Italian marble, shaped centuries ago by the sculptors of the Renaissance. In Florence, marble adorns the ornate campanile and Duomo. It was here in Florence that Michelangelo Buonarroti brought to life his unforgettable statue of the young David. The David stands next to unfinished sculptures known as the Prisoners. They are still struggling to come out of the rock. Michelangelo's sublime sculptures also guard the tombs of the powerful Medici family. He found the pure marble that he needed for his work in the Alpi Apuane Mountains, near the town of Carrara. The Alpi Apuane are so named for their craggy, alpine-looking peaks. Their dazzling whiteness can easily be mistaken for snow from a distance. But the white is not snow, it's marble. All over these mountains are quarries where huge chunks of marble have been extracted. These quarries remain the world's largest producer of marble.
Ancora da decifrare. Qua il problema è che c'è questa antiforme.
For geologists like Giancarlo Molli, a quarry can be an excellent place to study the insides of mountains. The rock layers have been exposed, making it easier to tell how they've been laid down, squashed, and folded. The hard marbles were created from softer limestone. It was in the limestone hills of Tuscany, around Florence, that Leonardo da Vinci found fossilized seashells. This was in the early 1500s, right at the time Michelangelo was laboring over his sculptures. When Leonardo found the seashells, it was not understood how they had gotten out of the sea and into the mountains. But over the years, scientists developed an impressive explanation. Millions of years ago, there was no Italy here. Instead, there was a shallow ocean called the Tethys.
The geologic story of Italy is really fascinating because you have to go back to set the stage. Before there was anything that we would recognize as the Apennine Mountains, there was the separation or the breakup of a large supercontinent called Pangaea. And in the breakup of this continent, a new ocean basin was created. We call this ocean basin Tethys.
Tiny sea creatures lived in the ancient Tethys Ocean. Over time, as they lived and then died, their remains drifted to the ocean floor. These deposits built up layers of sediment, miles thick, at the bottom of this sea. Eventually, the layers hardened into limestone. In the case of the Carrara marbles, the limestone was then buried deeply by tectonic forces over millions of years. Extreme heat and pressure baked it into marble.
The Carrara marble is a special, pure white marble. That is the reason why it was used by the Roman and then during Renaissance, for example, by Michelangelo, up to now, for monument as well as for building stone. And the fact that it is so pure is due to the fact that the original sedimentary environment was special.
That special environment was a warm, calm, shallow ocean, something like the Caribbean Sea of today. But to produce marble that is so pure and white, the original seafloor had to be well away from beaches and sand. But how did Italy's limestones, formed in the sea, end up as rugged mountains, rising far above sea level today? This question puzzled geologists for centuries. The place where the puzzle finally began to fit together was in one of the world's great mountain ranges, the Alps. A particularly dramatic part of this majestic range guards Italy's northernmost border. Piecing together the story of the Alps was extremely difficult, partly because of the vertical terrain and partly because the rocks of the Alps seemed all wrong. They were topsy-turvy. It wasn't until the 1960s and the advent of the theory of plate tectonics that the Alps began to make sense. About 80 million years ago, global tectonic forces caused the continents of Africa and Europe to approach each other. In between them, the seafloor of the Tethys, including a special piece of crust or microplate called Adria, dove or subducted beneath Europe. As this happened, great slabs of the Earth's crust and sediments from the sea floor were piled up into mountains at the edge of the European continent. In some places, older rocks were shoved over younger ones, obscuring their origins. Geologists climbing high in the mountains even found a piece of the Earth's mantle, which is normally buried 20 miles beneath the Earth's crust. The Alps were a geological mess, but a beautiful one. And from the unraveling of this mess, geologists answered the question of how seashell fossils could end up in mountains. When the continents collided, ancient limestones from the Tethys Ocean were thrust high in the air. One of the most dramatic examples of this action can be seen in Italy's Dolomites. Here, huge layers of limestone, once resting far below the surface of the sea, are now standing at great heights, draped in high mountain glaciers. Glaciers also carved out spectacular lakes, like Lake Como, during the Ice Ages. Armed with the story of the cataclysmic birth of the Alps, geologists began to explore whether this fantastic tale could also explain the birth of Italy's other great mountain range, the Apennines. Were these also pushed up by colliding plates? The story fit in many places, but in some it didn't. The Alpi Appuane range was one of those places where it didn't. Geologists could see that something far different must have made these mountains. But what was it? It wasn't until many years later that this mystery would be solved. There was another place in Italy that looked very strange to geologists. In the mountains of Calabria, at the toe of the boot, structural geologist Nano Sieber is exploring how this geologically perplexing area came to be. On the map, Calabria forms a link between the Apennines and the mountains to the south in Sicily. But the Apennines and the mountains of Sicily are mostly composed of limestone and other sedimentary rocks. In contrast, Calabria's mountains are made of granite and metamorphic rock, totally different from limestone. Over the years, Italian geologists puzzled over the strange rocks of Calabria, much as Nano Sieber is doing today.
In geology, that's what you need to do. You need to look at a mountain and think of what's in it. And not only that, but think how it changes the shape of the rocks inside the mountain.
It soon became apparent to Italian geologists that the odd rocks of Calabria extended into Sicily.
Controlled by these faults.
There was a part of Sicily, the northeastern corner, that was very different from the rest of the island. Here, at Messina, the rocks are more like Calabria's rocks and nothing like the rest of the Apennines. Close by, the Sicilian coastal resort of Taormina is also built on rocks like Calabria's. The rocks of the rest of Sicily fit with the Apennines on the mainland. What could explain these differences? It took a new twist to the theory of plate tectonics for geologists to figure out where these rocks had come from. And with that twist came a dramatic new understanding of all of Italy. It turns out that the rocks of Calabria and northern Sicily strongly resembled those of the Alps. And in fact, as Frank Pizzaglia learned from his Italian colleagues, these rocks had once been part of France.
Italy at one time was actually connected to France, and over the past several tens of millions of years, it has been swinging to the east.
Chunks of rock that would become Italy, along with Corsica and Sardinia, separated from France about 30 million years ago. Italy, still underwater, plowed into the Adria microplate, which subducted beneath it. In the process, pieces of Adria were scraped off, and a new mountain range began to grow. The Apennines were born. Initially, the mountains were below sea level. Finally, between 5 and 10 million years ago, Italy emerged from the sea. The subduction process caused a growing wedge of material that ran down the whole length of the Italian peninsula.
So Italy looks like a boot positioned to kick to the west, but in fact it is moving back towards the east, swinging and consuming the Adria microplate in its wake.
The swinging Italian boot that emerged from the sea solves Leonardo da Vinci's mystery about how the fossilized seashells got into the Apennines. But this fascinating tale of the birth of Italy and the Apennines was not yet the whole story. There were some very famous mountains in the south that did not fit this picture at all. Or did they? In southern Italy, above the fast-moving foot of the Italian boot, looms the legendary Mount Vesuvius. Mount Vesuvius is the only active volcano on mainland Europe. People come to see it from all over the world. During recorded history, Vesuvius has been known to erupt hundreds of times. The most famous eruption buried the prosperous Roman trading city, Pompeii, in 79 AD. Vesuvius is still active and could erupt at any time. Farther south, on Sicily, at the toe of the boot, is the massive Mount Etna. Like Mount Vesuvius, Etna is a very active and famously destructive volcano. For years, geologists could not explain what the two volcanoes were doing here. But around the time plate tectonics theory was established, in the 1960s, geologists came to a surprising conclusion about Mount Vesuvius and Mount Etna. They are volcanoes and completely different from the Apennines or the Alps. But they are actually caused by the same process, subduction. As the subducting plate sinks down, it slides under the other and heats up. This heated material becomes magma, which rises up through the top plate to build active volcanoes. the Italian volcanoes fit this picture well. In fact, geologists could trace a volcanic arc that follows the subducting plate, starting around Rome, where there are some dormant volcanoes, and curving down past Stromboli and the volcanic Aeolian Islands, and continuing past Etna farther south. But there was something peculiar about Etna. On a bright June morning, Nano Sieber and graduate student Margaret Reitz have come down from Calabria to get to the bottom of this peculiar feature.
Ooh, I think Giarre.
Yeah, there are a number of faults. Actually, we've got a north-northeast trend from the Strait of Messina.
Etna's eruptions contain a rarely seen mixture of lava and ash. Usually, a volcano produces one or the other. Why does Etna produce both? Nano and Meg have a new technique for finding out, but they must get the perfect lava sample. They have to work fast. The volcano has been erupting frequently, and the scientists are seizing this rare opportunity to find a sample before it erupts again. The going is difficult and even dangerous. Leading the way is Boris Benki of the INGV, Italy's National Institute of Geophysics and Volcanology.
The upper part of this vent erupted on the 10th of May.
Boris knows Etna as well as anyone alive.
Mount Etna is quite a large volcano and also one of the most active volcanoes on Earth. It's currently 3,330 meters tall. That's a little bit less than 11,000 feet. It's one of the most active volcanoes on Earth, maybe the second most active after Kilauea on Hawaii.
It's one of the most active volcanoes on the planet, and is very young, actually. It's only 500,000 years old.
How it got so big so fast is part of the riddle of Etna. How did so much lava accumulate so quickly?
Etna sits in a place where there are lots of faults and cracks running through the crust of this planet. In this very area, many of these fault systems intersect in that place. So it's a place of particular instability, and thus it is much easier for the magma to come at that place. There seem to be no other volcanoes on Earth where we have a similar geodynamic situation.
That looks good. Beautiful.
Now we can break that down further.
Yeah.
Finally, the team finds the perfect sample.
It's hard rock.
Okay, I'll mark
They will take it to the lab for analysis and find out that, indeed, Etna's lava is highly unusual. It often comes from very deep in the earth, working its way up through cracks. Nano's team timed their expedition perfectly. Shortly after their climb, Etna exploded. It's because Etna is so active that a huge network of seismic stations, gas monitoring devices, and other high-tech monitoring instruments has been set up to warn of impending eruptions. This warning system, one of the world's most advanced, keeps the 1 million people living close by safer. There are so many people living here because, as it turns out, there are multiple advantages to living on a volcano.
There are lots of benefits to life on a volcano because we've got very fertile soils due to the wealth of minerals in the volcanic products, especially in the ash. And everything that grows on Etna is a little bit bigger and a little bit more tasty. There are important resources like tourism. Then the volcano provides building material because the lava is very resistant rock, much better than concrete. And finally, also, the volcano stores incredible quantities of water because it's all porous rock. And that is certainly an important element in a place like Sicily where there are elsewhere problems with drought. If the southeast quake erupts again, we'll throw out a lot of old material.
As these scientists learn more about Mount Etna and volcanoes, They are also getting insights into an intimately related geologic process also caused by plate movements and subduction, earthquakes. People here have not forgotten the massive Messina earthquake of 1908, which caused widespread destruction in both Sicily and Calabria.
There's been terrible earthquakes in this part of the world, and understanding how Calabria works tectonically is going to help to understand what kind of earthquakes they can expect.
The people of Calabria and the rest of southern Italy are well aware that earthquakes and volcanoes are the geologic signatures of their land. Both are driven by the crushing tectonic force of subduction. But is subduction at work farther to the north? Is it a major force there?
Entire blocks of buildings collapsed as a powerful earthquake struck central Italy in the middle of the night. The U.S. Geological Survey says the quake measured 6.3 on the Richter scale.
In 2009, a large earthquake struck the central Italian town of L'Aquila, killing more than 300 people. About 100 miles away, in the region of Umbria, the 13th century Basilica of St. Francis of Assisi was severely damaged and 4 people perished when an earthquake struck in 1997. Obviously, the Earth's crust is very active in central Italy. Regions like Umbria and Tuscany are frequently jolted by earthquakes. But unlike the south, central Italy has no volcanoes. The line of subduction-driven volcanoes ends north of Rome. Is a process other than subduction building the mountains and triggering the earthquakes in central Italy? Until recently, geologists thought that subduction was long dead to the north of Rome. Apparently, another process, the stretching of the Earth's crust, had taken over. Or so they thought. But earth scientists working in central and northern Italy have begun to wonder. One of them is Mark Brandon, an old friend and advisor of Frank Pizzaglia. They are meeting in the medieval town of El Cito, from which they can see a long way off.
So we're looking along the entire Adriatic coast here.
Exactly, we're looking out over the top of Cingoli Ridge, and from Cingoli Ridge there's only one more limestone ridge.
Mark has been traveling around Tuscany, where signs of the stretching of the Earth's crust are much in evidence to geologists.
We see the rocks at the surface pulling apart. And a good example of that is that if we go into various parts of the landscape, like around Florence, what we see are there are big grabens or stretch marks where the earth is pulling apart at the surface. In fact, many of the earthquakes we see are due to a large part of the crust at the surface being stretched apart.
The lovely landscape of Tuscany near Florence is a familiar one, often used as the background in Renaissance paintings. Only a closer look by geologists reveals the wrenching apart of this gentle landscape.
You think Massa could go under here?
Traveling onward from central Italy and heading to the northwest, Mark Brandon and his colleague Daryl Cowan can tell that much more than stretching is operating to build Italy's mountains.
Yeah, Tuscan map.
One place where they're hoping to find the missing link is in Michelangelo's marble quarries in the Alpi Apuane Mountains. Waiting for his American colleagues at the station in Carrara is Giancarlo Molli with student Gabriel Casali.
Ciao.
Giancarlo is taking the group to his rugged, mountainous field area. Geologists have worked out that the famous marbles here have risen up very quickly from deep in the earth. And the only way they could have risen up so rapidly is if the rocks around them were being stretched apart by a very powerful and mysterious force. That stretching would have opened a gap for the Alpi Apuane to rise quickly to the surface.
Yeah.
it's possibly rejected.
The Alp area exposes the deepest metamorphic rocks in the Apennines. What we mean by this, these are rocks that have been taken deep into the crust and have been transformed by high temperatures and high pressures into entirely new rocks. And for many years now, there's been the recognition that the Apuani area and the metamorphic rocks that underlie it have been brought up to the surface by this overall stretching process. So it's a manifestation of this extension or stretching process, the deepest or most pronounced manifestation of that.
With the famous marbles of the Alpi Apuane fresh in his mind, Mark is impressed by what the stretching of the Earth's crust can do.
In the massa unit.
But what is the force behind the rapid stretching apart of tons of rock in the Alpi Apuane? And why is it that the Earth's crust in Italy is being pulled apart in some areas, while at the same time it's being squeezed up in other areas? Fortunately, Mark has studied mountain belts around the world, and one theory has emerged that makes sense to him. It's called rollback. In this scenario, the Apennines are being squeezed up into mountains above the downgoing subducting plate. Meanwhile, the subducting plate draws backward at the point where it curves downward. This is called rollback of the plate. As it rolls back, the subducting plate sucks the colliding plate towards it, stretching it apart. On top of that plate, the crust also stretches and deforms, rising up in some places and sinking down in others, creating a landscape of hills and valleys, as in Tuscany. But rollback has been hard to prove, and there are other theories that might explain the observations on the surface. This debate is what has brought Mark Brandon to Italy.
Italy is an exceptional place to study this process of collision of plates and overall stretching at the surface. We see this going on in different mountain belts, such as the Himalaya, the Andes. We also see it going on in submarine subduction zones like the Mariana in the Western Pacific. But many of those settings, either the process has been arrested or it's difficult to study directly because the topography is too high or we can't get directly to those areas.
The accessible topography of Italy's Apennines, with its network of good roads, offers one of the best hopes of solving this important geologic mystery. Geologists generally agree that the collision of the plates, followed by the subduction of the Adria microplate, pushed up the Apennines some 5 to 10 million years ago. But in one part of the Apennines, around the city of Bologna, many geologists were claiming that the mountains were now dead. They were no longer being pushed up by subduction. If that were true, then the rollback theory, which hinged in part on subduction still being active in northern Italy, was also dead.
It's 54, 40,000 or something. And right here it says in Marconi.
Hey, what's going on?
Well, she's got these really interesting offsets in the terraces.
You guys are worrying too much about the geology. Today is the feast of San Giuseppe, and it's traditional in many parts of Italy to have breads made on the feast of San Giuseppe, La Festa del Papa, and this is a serpentoni. We stuffed it with apples, and this is just a regular bread.
Frank and Mark have enlisted experts from various fields of earth science to find out if the Apennines are still alive or not. This is perhaps the biggest geological mystery remaining in Italy, and solving it will not be easy. The scientists are meeting to strategize at the Geologic Observatory of Col di Gioco, a tiny village in the northern Apennines. A number of the scientists are conducting experiments at the Earth's surface to determine if it's lifting up and deforming. Others are imaging the deep interior of the Earth.
In fact, there are.
Still others are mapping the bends and turns in rock layers brought up from far below.
That is the problem that we would like to.
One member of the collaboration is geologist Vincenzo Picotti. Vincenzo has been working on the Reno River at a town called Marzabotto, not far from Bologna. Here, a novel technique has been used to calculate the ages of the terraces above the river. On top of these terraces are artifacts of the ancient Etruscans that once lived here. On one wide, flat river terrace are the ruins of an ancient Etruscan town. Since archaeologists know exactly when the Etruscans lived on this terrace, Vincenzo can use that date to establish that the river terrace is at least that old. This will help him see if the mountains are still growing.
This is a village of Etruscan age, and those walls we can see now are the foundations of the houses of this highly civilized people. The age of this village is more or less 2,500 years, and so we can have a minimum age for the river terrace.
Soil geomorphologist Missy Epps is using a different technique. She is establishing the ages of river terraces that may be hundreds of thousands of years old by looking at the soil on top of them.
Soils work much like people work in terms of the older they get, they have certain characteristics that enable you to understand how old they are. Just like a mom might be able to look at any child and know that it's, 15 weeks or a year and a half or, 3 years, and you use the characteristics of that child to say how old it is. Well, we do the same thing with soils. The older soils get, the redder they get, the deeper they get, the more clay they have in them. Well, actually, so that I can go up to an outcrop and look at a nice exposure of a soil and say, this much reddening, this much clay, it must be 10,000 years old. This soil is really thick, it has a lot of clay, it must be 100,000 years old. Oh, that's nice. This is where I was having all that trouble. If this were the QT6 strat, then there'd be a lot of offset. So if we could find a soil right there, then we would really know.
Once Missy and graduate student Ryan Bierma find ages for the river terraces, they can look to see if there are terraces of the same age but of different elevations. If they find those mismatched terraces, it means the Earth's surface is deforming here. Or, in other words, the Apennines are still alive and growing.
Yeah,
Okay, wow, wow.
yeah.
Meanwhile, the scientists have found yet another way to learn from the rivers if the mountains are rising or are now dead.
One very critical data set that we are collecting is related to the rate at which rivers are carving their valleys and vertically incising into the Apennines. Because the rate that rivers incise into mountains is related to the rate that the rocks are coming up.
That is, if they are coming up. While Frank is working on understanding vertical motions, elsewhere, horizontal motions are being measured. In the tiny independent republic of San Marino, scientists are measuring how the Earth's tectonic plates are moving in northern Italy.
You can't be afraid of heights and run this network.
No.
Here, geodesist Rick Bennett and his Italian colleagues have installed one of their GPS antennas.
In this project, we're installing antennas such as this one in as many locations as we can find throughout northern Italy. The idea is that we'll be able to determine the motion of all of these instruments, and from that information we'll be able to learn about how the Italian peninsula is responding to the relative motion between the Africa plate, the Eurasia plate, and the Adriatic plate.
In the course of a year or two, the GPS antennas should detect movement, even a tiny movement, if the mountains of northern Italy are still growing and pulling apart. It may even be possible to tell if the entire peninsula, the boot, is still swinging back, getting ready to kick.
Shall we try?
Try, yeah, sure.
Just take up
But it's not always easy to find the best spot to install these antennas. Fortunately, for this one, a colleague has volunteered his roof.
It's been very difficult to find good locations to put these instruments. They require sky visibility so that they can actually see the satellites. They require solid bedrock so that we can be confident that they're firmly attached to the Earth's surface. And there are not many places in northern Italy with those characteristics. So we've had to resort to some rather unconventional ways of attaching the antennas to the Earth. In some instances, we've actually put the antennas on ancient castles that have been around for 800 years or so, which are now possibly part of the Earth's surface.
All of these geologic studies generate huge amounts of data. Most of it is a pile of numbers, hidden in computers and never seen, even by the scientists working on them. But that data will form the basis of important new scientific discoveries. And occasionally, something else. Music. At Col di Gioco, Sandro Montanari, the director of the Geological Observatory, has built a recording studio with the help of composer Gabriele Rossetti. The two colleagues are taking geological data and turning them into notes and music. One of their compositions is based on data from a world-shattering event discovered in some rocks not far from Col di Gioco. Here, a thin layer in the rocks gave scientists the first clue that it was a giant meteor striking the Earth that spelled the end for the dinosaurs. Today, Sandro and Gabriele are working on another piece called Gocce di Tempo, Drops of Time.
These are plots of carbon and oxygen isotopes that have been taken from the Frasassi Gorge. And the variation of these values tells us how the environment was changing through time for the past 100,000 years.
This music reflects the chemistry of formations in a series of magnificent caves, the Frasassi Caves. These caves are made of limestone, which was born 100 million years ago in the Tethys Ocean. Tiny drops of water have dissolved away the limestone to sculpt more than 100 caves at Frasassi. Besides being a wonderful source of musical composition, the Frasassi Caves hold important geological clues about the growth of the Apennines. Sandro Mariani, who's been working with Frank Pizzaglia at the Mazzoni River, is an accomplished cave explorer. His nickname is Spider-Man. Sandro is using a leveling instrument to see if the rock layers in the cave have been tilted. Tilting would mean that the rocks were bent as the mountains grew. And sure enough, Sandro finds bent rocks in the caves. This is evidence that the mountains have been slowly growing through the eons. Going deeper still, scientists are interested in knowing what's happening far below the Earth's surface. To see many miles down into the Earth, seismologists Silvia Pondrelli and Jeffrey Park are installing seismic instruments in the mountains.
I think that seismology is going to be pivotal in determining the best explanation for the Northern Apennines, because it's seismology that allows us to see beneath the surface, beneath the crust, and into the mantle where the action is.
Their biggest question is this: is the Adria microplate still subducting, causing the Apennines to grow? Or are other processes involved in building the Apennines? Jeff and Sylvia will use waves generated by earthquakes to see if they can find the answer in the deepest roots of the mountains. While Sylvia, Jeff, and their colleagues work to find out whether northern Italy is still alive geologically, in the south there is no doubt. Striking evidence for this is found at the Adriatic coast in an area called Apulia. Here, at the heel of the Italian boot, instead of mountains, there is a mostly flat, level coastline. Seaside resort towns like Trani line the long curving bays of the coast and look out upon the gentle waves of the Adriatic Sea. Dotting the countryside are round stone huts called trulli. There is a concentration of trulli in the town of Alberobello, a UNESCO World Heritage Site. These whitewashed huts are built of limestone, which forms the bedrock of this unusual part of Italy. Limestone has been more than the stuff of building blocks in Apulia. In the town of Matera, people once actually lived inside the limestone, carving their dwellings into the limestone cliffs running below the city. These dwellings, dating from medieval times, are known as sassi. But why is Apulia so different from mountainous Calabria? It turns out that in the complex geology of southern Italy, Apulia is yet another microplate that was once a part of Africa.
About 10 million years ago, Calabria and Sardinia were together, and Calabria decided to go alone. So it took off from Sardinia and moved southeast. And in doing so, it created the Tyrrhenian Sea and collided with an old piece of Africa, which is called Apulia.
Originally, Apulia was under the sea, a gentle seafloor made of limestone. It was pushed up above sea level by its collision with Calabria. Apulia and Calabria sit on opposite sides of the Great Subduction Zone that created Italy, where the African and European plates collide. The collision zone sweeps right through the heart of Sicily.
See another volcanic interval.
Mark Brandon and his colleague Carl Wegman have come down to Sicily to see if the subduction zone here can tell them something about subduction in the north. They are guided by one of the leaders of Sicilian geology, Fabio Lentini.
Interesting. You see here?
Yeah.
Yes.
Wow, look at those
These
corals.
are colonial corals, Docora cespitosa.
They start their reconnaissance in northern Sicily. This part of the island is defined by mountains. They hug the coast and protect ancient cities like Cefalu and the Sicilian capital Palermo, once the greatest city in Europe. The geologists stop frequently to study the limestone mountains pushed up by the power of subduction. As Mark and his colleagues reach central Sicily, the mountains thin out, becoming isolated sky islands, topped by towns like Enna and its medieval rival across the valley, Calascibetta.
I don't recognize the place.
A little further south, the landscape flattens suddenly. This is the African plate, and half of Sicily sits on this plate. The soils and bedrock of southern Sicily are best seen along its breathtaking coast. They come in shades of white. Ragged limestone terraces make for cozy alcoves and secret harbors. This one, north of Syracuse, was once a pirate hangout. Salt and gypsum mines are everywhere. These minerals speak of a remarkable time about 6 million years ago, when tectonic forces blocked the Strait of Gibraltar. The ancient Mediterranean Sea was cut off from the waters of the Atlantic, leading to what geologists call the Messinian salinity crisis.
The whole Mediterranean dried up. It was a big, deep hole where we now have water. And as it dried up, all of the salt and other dissolved constituents came out as thick evaporite units.
the deposits piled up on the dried-out seabed. Later, ocean water flooded back in again and covered them up. Now, as the African and European plates continue to collide, those seabed deposits are slowly rising out of the sea. Farther south, at the southernmost part of Sicily, stand the spectacular Greek temples of Agrigento. Near Agrigento, the coastal rocks clearly show the effects of the incoming African plate. There is no doubt that this part of Italy is geologically alive and kicking.
You can see the ocean out to the south of us, and further on is Africa, in fact, Tunisia. And in this area, we're looking at the very beginning of the collision between Italy and Africa. And in this collision zone, there are a bunch of rocks that are crumpled up. You can see them folded in the background over here, and they represent marine sediments, in part, that were originally in the ocean to the south of us and have been squished as Italy has come colliding with Africa.
Tunisia is close to Sicily, only 60 miles away. So Mark and Carl have come down to explore the collision zone from the African side. Tunisian geologist Sami Komsi takes them on a tour of the mountainous countryside.
There should be more.
Geologists have worked out that these rocks in northern Tunisia are actually an extension of the Apennines. They were created by the same subduction zone that created Italy. The subduction zone curves down from Sicily to bunch up the Atlas Mountains in Tunisia. The rocks here announce the collision situation loud and clear. They are tightly folded and broken up in many places. But in northern Italy, in Frank Pizzaglia's field area, there are no such obvious clues. So scientists are patiently plying their trade, gathering data. Finally, a breakthrough comes near Bologna. It comes unexpectedly from the detailed mapping of the river terraces and the soils on top of them. The scientists find faults caused by earth movements breaking up the terraces. Finding fresh, active faults helps prove that the Apennines are indeed still alive and growing. Frank's nagging question has been answered.
A very exciting result that's emerging from our collaboration is that, in fact, the mountain front at Bologna is tectonically active and is continuing to grow.
Oh, look at there.
The data are very compelling, and we're very excited by this conclusion.
Other results take a few years longer. Rock samples from the Alpi Appuane reveal that here the mountains have risen up from the depths with unusual rapidity, about 1/3 of an inch per year. This is very fast geologically, and probably could not have happened if the crust were not being pulled apart so strongly in northern Italy. To top off these findings, GPS studies also show that the Apennines are indeed alive and moving horizontally in some areas. The data indicate that in some parts of Tuscany, the Earth's surface is splitting apart about 1/6 of an inch per year. The data also show that the Italian boot is still swinging back as if to kick.
Converging downstream here.
Yeah, I think that it comes through where this fault runs.
All of this evidence fits well with the theory that rollback is occurring in Italy. The seismic studies clearly show that the Adria microplate has sunk deep into the mantle. This has happened over millions of years, both squeezing the Apennines upward and pulling them apart. It's a process that balances two opposing forces, and likewise its impact on people can be seen as both beneficial and harmful. Earthquakes and volcanoes can cause tremendous damage, but they also make for a beautiful, bountiful land. Without tectonically active, growing mountains, the great marble of Carrara would never have seen the light of day, and the art of the Renaissance might have turned out very differently.
Downstream, this point of rock comes right out here.
Meanwhile, Frank Pizzalia and his colleagues have been adding their own brushstrokes to Italy's complex geologic portrait. It's an elegant and unusual portrait, and like Michelangelo's unfinished prisoners, it's not yet complete. Working on Italian geology is a challenge, certainly, but delightful, like so much else in Italy.
I always laugh because no one ever feels sorry for you when you tell them that you have to go do work in Italy.
It's a wonderful place to work. It's got beautiful weather, beautiful scenery.
It's very fertile because it's active. It's very beautiful because it's active. The reason that Italy is what it is because tectonically it's an active place.